Okay, so this Durbin-Watson test then, so this is a classical test in econometrics, and this is the classical test that is used to gauge whether or not there is autocorrelation in the residuals of a regression model. So the question this asks is, what proportion of the residual sum of squares can be explained by the correlation between successive residuals? So equivalently, sum of squares just means information, so this is just what proportion of information in the residual sum of squares can be explained by the pairwise correlations in the residuals. And said there that it's sort of important historically. Now I think this is sort of true when I was writing these slides, I'm less convinced this is true now. So my experience suggested in the past tense that the Durbin-Watson test is impractical for large problems. Now I would suggest it's probably impractical for large problems if you're using eViews, but actually I think it is more practical if you're using R, and I think this is one of the first examples where if you use a higher order programming language like R, it's actually easier to do something slightly challenging like this Durbin-Watson test than if you're using something like eViews, which is in contrast primarily menu driven. So the first time is actually worth using something harder here, our Durbin-Watson test. So the Durbin-Watson test is important historically, and it's also a popular econometric approach, and it is defined, this Durbin-Watson statistic, as the sum of the square differences in successive residuals relative to the residual sum of squares. So if you're looking at this fraction in the right way, this is measuring what proportion of the residual sum of squares can be explained by the squared distance between successive residuals. Okay, so this is just asking how much information in the residual sum of squares that can't be explained by the model can be explained by the pairwise correlations between successive residuals for this regression model. The sense in which this is logically constructed then is you're trying to measure this ratio in the first equation, and conventionally how this test was performed was using statistics tables. However, it's actually much easier if you use R to program this test. Okay, and as we sort of will show later in the lecture, you can use R to actually do this test even when you've got large sample sizes. So there are a number of classical assumptions that underpin this Durbin-Watson test. These are discussed in this chapter here in Gujarati and Porter. So the idea is that the regression model includes the constant intercept term, the x variables are non-stochastic. The assumption is that the residuals term in the regression are autocorrelated of order 1. So this just means that there's a very precise form for this autocorrelation. Okay, so one example of this might be if you look at the example with the gold prices and the stock prices, the interpretation of this would be that the residuals in, for instance, the year 2000 and the year 2001 would be autocorrelated. This isn't necessarily an assumption to make in step 3. Assume that the error term is normally distributed, and that the regression model does not include large values of the dependent variable on the right hand side. Also assume there are no missing observations in the data. Okay, so I ought to just sort of recap that assuming you've got this first order autocorrelation, perhaps you shouldn't interpret this too literally. It's just natural to assume that residuals for successive terms would be correlated. So for instance, residuals for year 2000 and year 2001. So historically, the Durbin-Watson statistic and the test relied on quite complex statistics tables. Okay, I think actually it's much easier to run the test in R, and if you run the test in R, you don't have to worry about statistics tables like this. But I think if you run the analysis in eViews, it's actually not very clear as to how to best interpret the Durbin-Watson statistic. Okay, so in certain circumstances, this gets trickier than you might imagine with large sample sizes. So there's various different scenarios there. So there's possibility that you can reject the null hypothesis of no positive autocorrelation. You're also not necessarily able to make a decision on whether or not there's positive autocorrelation or negative autocorrelation, so the test can get rather difficult to interpret in some senses. You can also reject the null hypothesis of no negative autocorrelation, and you can not reject the null hypothesis, so you'd accept the null hypothesis of no autocorrelation if you have the final scenario in the bottom slide. Now, I'm not convinced this is the best way of presenting this information, but just to sort of point out here, it's not necessarily automatic how to interpret the results of this test. So the conventional approach then is tricky. I believe it's probably easier to perform this test in R, and then if you do the test in R, you don't have to worry about any statistics tables. But what you have to do here, in order to run the Durbin-Watson test in R, is to load this R package LM test. This stands for linear model test. A linear model is just an alternative way of saying regression model, so you need to run the sort of standard regression tests and this R package here, LM test. To do that, once you've loaded the package, the function that you need is DW test, which stands here for Durbin-Watson test. Okay, so these things are logically named, and the idea would be that you would run the regression model in the usual way, and then you would apply this DW test function to a named linear regression model object. So for instance, if you've got this thing here, A.lm, for the real gold price, real stock price example, you would apply the DW test function to the A.lm linear model object. So the results are relatively straightforward to interpret in this case. So it gives you the Durbin-Watson statistic and then the p-value, which is less than 0.05, and as it says there's evidence from this Durbin-Watson test is positive autocorrelation in the residuals. So similar to the previous lecture examples then, the standard regression theory and programs assume that regression residuals are uncorrelated. So if you have autocorrelated residuals, you won't blow up your laptop, you just may not be able to trust the computer generated results at face value. So what we've got in this example are, it says there, slides 3.6 and 3.10, where you've got graphical evidence that the residuals for this regression model are correlated. Alongside that, we've now got formal statistical evidence that the residuals are correlated. And I think the thing to emphasize here is that you've got both graphical evidence and statistical evidence telling you the same thing. So they're serving as a cross-check of each other, and this is a really big deal that you've got these two different pieces of information telling you the same thing when it comes to real projects. You also know in this case, from the wider context, that since you've got financial prices collected over time, it's likely that you're going to get autocorrelation in the dataset as an artifact of that. So this is a practical problem whenever you collect, say, financial data over time, and there's two possible solutions presented here. The first one, probably the best one, is to fit regression models with autocorrelated errors. The second one is this Newey West HAC correction. It's not necessarily, this is a it's not necessarily easy to understand how they work. So if you wanted to do regression with autocorrelated errors in R, the basic R command that's needed is something called ARIMA. Now this is important here because the name ARIMA indicates that what you've got is some combination of regression with an element of time series, and the way this would work, so you want ARIMA Y variable, the xreg command lists the x variables, and then the order of the ARIMA model. And there might be a closing bracket term that's missing from the slides. So in the xreg part, what you would do is specify the regression formula to be used, and then for this module, when you order bit, what this is doing is specifying the order of the ARIMA bit, and then for this module we're only interested in fitting an autoregressive model of order 1, so you would just need this to be 1, 0, 0. So the method can be applied much more generally, but for this module you just need the simplest possible model here, autoregressive model of order 1. And so how this would work then for our lecture example, so the y variable is real gold price, the x variable would just be the real stock price, and the order would just be 1, 0, 0, again to just emphasize that you're fitting a first order autoregressive model to the residuals. So how this works then, the analysis in R, it produces the estimates and the estimated standard errors, but you have to do the t-statistics yourself, unfortunately. So the set of R output there, the estimates and the estimated standard errors. Now the length of the gold price is 33, so this tells us we have 33 minus 3 estimated parameters, so 30 residual degrees of freedom. In this case, you calculate the t-statistics as follows. So the first line of bit here, coef, is just the from the first line of the ESE is just the second line of the output, the estimated standard errors, and then all you would do to calculate the t-values, the t-value is just the absolute value of the coefficient estimate, estimated standard error. Sets of t-values are shown there at the bottom of the slide. Okay, so what you have is the term, the then the intercept, and then the coefficient of the real stock price. So in eViews, fitting a regression model with autocorrelated errors is just an extension of what you've seen before. And just to recap, that a regression model with autocorrelated errors is probably more practical and preferable to doing this Newey West correction. So what you would do with the eViews work file that's on Canvas, so you put the regression as normal, quick equation, and then enter real gold price, C, real stock price, but in this case, after the real stock price, you need space and then AR1, which would specify an autoregressive term of order 1 to be fitted to the residuals. So this is exactly the same as we've done before with the regression examples, but we've added on now an additional AR1 term precisely to account for autocorrelation in the residuals. Now essentially everything in the regression model works exactly the same as before, so the interpretation of t-statistics, etc. remains the same. It's just that we're allowing now for the fact that you might have, say, some autocorrelation between the residuals for year 2000 and the year 2001. Okay, and as we said before, it's very common that you get autocorrelation like this whenever you've got a data set where you're collecting financial price data over time. In terms of the interpretation of the results then, so the t-statistics a couple of slides ago give evidence of autocorrelation in the residuals. The p-value is 0.1235, so 5. This autocorrelation then reflects the fact that it's harder to establish a genuine link between real gold prices and real stock prices than might be first thought, and also I think it reflects the fact that you're going to get a certain amount of autocorrelation precisely because you've got price data in this example that is collected over time. You've got weak evidence of relationship between the real stock price and gold price, and this is probably the best way of interpreting this in some sense. You just can't be sure. Now, the standard way of interpreting this for a coursework or for the exam would just be to tell me whether or not P is less than 0.05 or greater than 0.05, but it's not necessarily always as nice and easy as this, and in this case we're sort of in the corridor of uncertainty, and whilst you can still do very well on the coursework assignment by just telling me whether or not P is less than 0.05 or greater than 0.05, just beware sometimes the interpretation of these things can be more nuanced with a real data example. I have, for instance, had an MSc dissertation student in the past who didn't do a great job of interpreting results that were weakly significant like this.